Across the deep field of the solar system, an item that ought to have been constant isn't. The interstellar object known as 3I Atlas has begun to drift off prediction. Its trajectory is flattening. Its speed bends in a curve downward, as if an invisible force had gripped it in the void between planets where no drag or field exists. 3I Atlas is sluggishing. So the question, this interstellar visitor is not where it should be. Where did it come from? And what, exactly, is attempting to stop it? The age problem. Among the many plotted trajectories across the night sky, one path refused to bend. The object now catalogued as 3I Atlas entered the solar system on a course that was to fast its velocity exceeding escape speed by a wide margin. Its motion was to straight, to certain, to belong to anything born under the sun. The calculations confirmed what the geometry implied. This body came from space between the stars, carrying the momentum of a different system or maybe another era entirely. When its orbit was projected backward through galactic coordinates, the track failed to intersect with any known stellar neighborhood. Instead, it passed through a region between the Milky Way's thin and thick disks, a vast transitional zone where stellar density drops and orbits become tilted, ancient, and quiet. That emptiness raised a single conclusion: 3I Atlas had been traveling for millions, possibly billions of years. Nothing had deflected it. Nothing had claimed it. The thing's composition reinforces that sense of age. Spectral sampling from ground-based observations made it clear. A variety of carbon-bearing volatiles and high-albedo materials, substances that ought to have degraded into dust under constant cosmic exposure, were still intact. Yet their signatures have not changed, suggesting that 3I Atlas spent most of its existence shielded from intense radiation, perhaps drifting in the cold outskirts of a long-dissolved system. Preservation on that scale implies formation in a young chemical environment, one poor in heavy elements, but rich in pristine ices. Every parameter, its exaggerated hyperbolic speed, its indicators of low metallicity, its unaltered volatiles aligns with an origin predating the solar system itself. It may represent matter condensed when the galaxy was still coming together, a small piece of the early interstellar medium locked in ice and dust. Now, within the briefest moment of cosmic time, that fragment has crossed the sun's domain, reflecting light that was never meant to touch it. There is no parent star to trace, no gravitational signature to come. 3I Atlas moves through our system not as a tourist with a destination in mind, but as a survivor of galactic history, an object older than the world observing it, still carrying the temperature and silence of the time before stars like ours were real. The lost star theory. When 3I Atlas's motion was extended backward through time, the results produced not a lineage but a void. In every computational model, its path slid through the space between stars without interference from the gravity of any known sun. 60 potential encounters were tested using Gaia's stellar motion data. None resulted in a gravitational match strong enough to redirect an object of this velocity. The implication was unsettling. 3I Atlas had not been ejected recently from a planetary system at all. It had drifted long enough for its origin to vanish from the maps of the evolving galaxy. That realization led to a new interpretation of its birthplace. Beyond the Milky Way's spiral arms lies the region between the thin and thick disks, an area of transition where the orbits of old stars tilt out of alignment with the galactic plane. It is a sparse environment, neither part of the youthful thin disk nor fully bound to the relic halo created when the galaxy first came together. Stellar encounters there are rare, gravitational tides are weak, and isolation is nearly indefinite. An icy body released in that region could drift for billions of years without much deflection, maintaining its course until the galaxy itself turned beneath it. The kinematics of 3I Atlas support this view. It has a greater galactic velocity than the average thin disk population, but lower than typical halo objects, placing it squarely in the middle range. Its inclination relative to the galactic plane, as well as its chemical signs of low metallicity, suggest it formed among the ancient population at that boundary. If so, the object represents material forged before the Milky Way's youth, before successive generations of stars enriched the interstellar medium with heavier elements. In that context, 3I Atlas becomes less a comet and more an artifact, a frozen remnant from the formative period of the galaxy, a time capsule of early cosmic chemistry. Its untraceable path does not imply mystery for the sake of drama, it demonstrates actual absence. The child star that once held it, if it ever existed, has likely aged beyond recognition, its light diffused into the general glow of the Milky Way's oldest disk. The only thing left is 3I Atlas, the ghost of the early galaxy. If 3I Atlas truly emerged from the frontier between the thin and thick disks, then its existence is more than an astronomical coincidence. It is a direct sample of an older Milky Way. That region is often described as a transitional membrane in galactic evolution, where the populations of stars overlap in both age and motion. The thin disk carries the metal-enriched younger generations' elements recycled through countless supernovae. The older, thicker disk holds rougher stars, forged in the galaxy's first chaotic billion years, when dwarf galaxies collided and turbulent accretion sculpted its form. Between them lies a gravitational buffer,